Dr. Ranjani Parthasarathi is a professor in Department of Computer Science and Engineering. Her area of specialization is in computer architecture and computer networking. She had guided more than 5 PhD students and currently guiding 5 PhD students. She had published paper in more than 50 national and international journals. She worked in many sponsored projects and she got IBM Faculty Award for 2008.
Welcome to the UGC lecture series in computer science. We are looking at a series of lectures in computer networks. We have been looking at local area networks. Today we will be looking at wireless local area networks, or WLANs as they are called. So today's topic would be on wireless LANs. We will look at the media access problem that exists in wireless networks and the solution to the media access problem. And we will look at it from the context of the 802.11 standard, which is the most common standard that is used for wireless LANs. So if you look at the IEEE 802.11 protocol, there are a wide range of uses for this standard. It is used for networks which are constructed, wireless networks constructed with infrared signals within a building, can be used for mobile computing, can be used for constructing a network of low flying satellites and so on. Coming to the physical properties of the 802.11 specification, the specification allows running over 3 possible media. One is radio using frequency hopping, radio using direct sequencing, and it also allows for infrared over short distances for about approximately 10 meters. So if you look at the standards that we have, you have the physical layer below and you have upper layers on top, and if you look at the MAC, the media access control mechanism, you have 802.11 with FHSS, which is frequency hopping spread spectrum, 802.11 DSSS, which is direct sequence spread spectrum, and then you have orthogonal frequency division multiplexing and so on. So to understand what we mean by this 802.11, 11E, 11B and so on, we just need a little bit of digression into spread spectrum radio. So we will just take a look at what we mean by this spread spectrum radio. So if you look at spread spectrum radio, the purpose is to spread a signal over a wide frequency range so as to minimize interference. Typically military uses this for anti-jamming. So in military, typically what you do is you keep sending data over a wider range of frequencies so that if you have an adversary, they are not able to track and lock into your signal and get access to your signal. So this is something that is used for anti-jamming purposes. So the signal can be used in a very noisy environment and still get through. So that is the idea of using a spread spectrum radio. There are 2 mechanisms that we use for achieving the spread spectrum, that is to spread the frequency wire over a wider, to spread the signal over a wider range of frequencies. So let us look at what happens in frequency hopping first. This is a very simple technique. So what we do here is you transmit the signal over a pseudo-random sequence of frequencies. First you transmit on one frequency, then a second and so on. The sender and receiver are using the same random number generator, so they can stay in sync. So you can get the idea here. What we are doing is the sender will transmit on a wide range, on a set of frequencies, on a random set of frequencies. The receiver also will receive on the same random set of frequencies, but you keep moving from one frequency to another. So this kind of a frequency hopping is also something which is used in military. Again, the genesis for this comes from the military applications. So you keep shifting frequency so that you make sure that the other person is not able to, in the case of military, you are preventing another person from not knowing the sequence, therefore they are not able to lock onto your signal. When we use this for regular transmission in WLAN, both the sender and the receiver know the set of frequencies that are to be used, so they will lock onto the frequencies and they will get the signal that is being transmitted. So this is the idea that is used. So you are able to spread out over a larger range of frequencies. And what the specification specifies is that it says that you use 79 different 1 megahertz wide bandwidths and you spread the signal across these different frequency bandwidths. So this is what happens in frequency hopping. So now if you look at direct sequence spread spectrum, this is another interesting technique. What we do here is each bit of data is replaced by multiple bits in the signal. So and how do you replace it by multiple bits in the signal? The transmitter sends the exclusive OR of the data plus a set of n random bits. So each bit now will be transmitted as n bits. Now how do you generate these n bits corresponding to the signal? You have a set of n random bits. Again, both the sender and the receiver know the random sequence that is used. So the receiver can use the same set of n random bits and recover the signal from this. And since we are using an exclusive OR function, if you again do an exclusive OR with the same set of random bits, you will recover the original signal. That is the idea that is used in direct sequence spread spectrum. Let us take an example of this. So, if you look at the picture here, you will find that okay, this is the signal that I am transmitting. A is the data stream that I want to transmit, 1 0 1 0. I have a 1 0 1 and a 0. Now, B is the random sequence that I am using. So, let us say I use a random sequence of 0 1 0 0, 1 0 1 1, 0 1 0 1, 1 0 0 1. I am using 4 bits for every single bit that is being transmitted. So, the XOR of the two will be the actual direct sequence spread spectrum signal that is generated. You can see that this will have more number of transitions than the original signal and will occupy a higher frequency bandwidth than the original signal. So, this is how you spread the signal over a wider band of frequencies. So, this is the idea that is used in direct sequence sequence spread spectrum, and you can see what will happen at the receiver side. If you look at the receiver side, if you get back to the picture, you can see that what I receive will be the XOR, this is what I will receive, and I know this random sequence. So, I do an XOR of these two and I get back my original signal. So, this is how the direct sequence spread spectrum technique is used. Now, coming to the media access control, that was about the physical layer. Now, we are looking at the media access control. Coming to media access control, the question that we have is, now we are already familiar with the media access control that works for Ethernet networks. So, what do we use over there? We have the CSMA CD, carrier sense multiple access with collision detection. Can the same scheme be used in the case of wireless networks also? The reason why we think of using the same scheme is that in CSMA CD Ethernet, that is also a broadcast media, and wireless networks are also a broadcast media. So, if CSMA CD will work for Ethernet, the question is, will it work or not for wireless networks? So, let us look at whether it will work or not. So, the question that we have is, can the CSMA CD of Ethernet work? The answer is not really, because it is little more complicated than in the case of an Ethernet network. In an Ethernet network, all the nodes get to hear the signal of all the other transmissions, whereas in a wireless network, you will find that not all nodes can see and hear each other. So, if you take a look at this picture here, I have 4 nodes A, B, C, D. So, what we are showing here is basically the range of each of these nodes. Okay, let us say for instance, B has a range which is shown by this blue circle here, C has a range which is shown by this yellow circle over here. Now, you can see that C's transmission will not be heard by A because A is totally outside of C's range. So, similarly, D will be outside of B's range and so on. So, because of this, if A is doing a transmission, D will not know that this transmission is happening. So, the idea of doing a collision detection by listening to the media and finding out that okay, there is a collision or the two people are transmitting at the same time will not happen over here, and this can lead to problems. So, let us look at the typical problems that occur in this scenario, and then we will look at the solution to that. So, let us take a look at this problem. So, let us say A and C send a signal to B, that is we are looking at the same situation that we have here, right. You have A and C wanting to send a signal to B. Remember that A cannot hear C's transmission, C cannot hear A's transmission. Therefore, A and C are both trying to send a signal to B. So, let us look at what will happen in that situation. A and C send a signal to B, but A and C are not aware of each other's signals. We have seen that. So, the signals obviously will collide at B because both the signals are coming into B. Now, but A and C do not know they collided, so they can't do collision detection and avoid the collision. Okay, they can't do collision avoidance by going into an exponential back off any such mechanism. So, A and C do not know that the collision has taken place. So, the collision detection or the collision avoidance of A that is done in the CSMA CD cannot work in this case. So, what we say here is A and C, we refer to them as hidden nodes, that is A and C are hidden with respect to each other. So, this is a typical hidden node problem that we talk about in a wireless LAN network. Okay. So, let us look at another problem that can occur over here. Let us say B is sending to A and C can hear the signal from B. Okay. So, B, remember that both A and C are within the range of B, right. So, because A is on one side, C is on the other side. So, when B is sending data, both A and C can hear it. Now, B is sending to A, C can hear the signal from B, alright. So, now in that situation, let us look at what happens. Now, since C can hear the signal from B, C will sense the media, it finds that it is not free. So, C assumes that it cannot transmit, so it will not transmit. But C could in fact transmit to D because C's transmission to D will not interfere with A's reception of the signal from B, right. So, C could in fact transmit to D, but you will not transmit. That is, you can actually transmit, but you will not transmit. In the previous case, you should not have transmitted, but you transmitted, right. So, that was a hidden node problem. This problem that we have here is called as the exposed node problem, right. So, we have a hidden node problem in the first case and now we have an exposed node problem. So let us just look at it again pictorially. You can see on the left side what I am showing is a hidden node, hidden station problem, that is A wants to send to B but cannot hear that B is busy. C is transmitting, assuming that C is transmitting. A wants to send to B but cannot hear that B is busy, therefore it goes and transmits. A and C are hidden with respect to each other. On the right side we have the exposed node problem. Here what is happening is B wants to send to C but mistakenly it thinks that the transmission will fail. Suppose A is transmitting to somebody else. Okay. Now if B wants to transmit to C, B will not transmit because it thinks it is going to collide with this, right. So you have this case of an exposed node problem, exposed station problem. So these are two main problems that we have in the 802 in the wireless network. So let us look at how 802.11 solves this problem. So what we do here is we go for collision avoidance. Rather than looking for collision detection, we take a different approach and we go for collision avoidance. So look at what is this collision avoidance. So we have a protocol now which is called multiple access with collision avoidance, okay, MACA or the MACA protocol as it is called. So let us look at what happens in this collision avoidance. So what we do here is the sender and receiver exchange certain control frames before they actually begin transmission. So the transaction goes like this. Sender A will send what is called as a request to send to the receiver, which is B, okay. So A sends a request to send to receiver B. B sends back a clear to send or a CTS frame. Okay, you have an RTS frame going from A to B and you have a CTS frame to send back by B to A. Now what happens is then A will send the packet. B sends an acknowledgement after receiving the frame. So you have RTS, CTS, then data and then an acknowledgement for the data that was transmitted. Okay, so let us look at the logic and see how it will avoid the two problems that we talked about, the hidden node problem and the exposed node problem. Okay, so let us look at this logic. So if a node hears the CTS, it knows that it is near the receiver, so it does not transmit. Okay, I first sent an RTS and then I am sending a CTS. So if a node hears the CTS, it definitely knows that it is near the receiver because it is a clear to send that is coming from the receiver. So on hearing a CTS, it knows that it is near the receiver, so it cannot transmit. Okay, so it will not transmit. Okay, so that will avoid our hidden node problem. Then if a node hears the RTS but it does not hear the CTS, which means it is not near the receiver but it is near the transmitter. So now it can start its own transaction. This takes care of our exposed node problem. Remember what happens in the exposed node problem? I could have transmitted but I did not transmit. Now in this case B, let us say B is transmitting to A and C hears B's transmission. So B would have heard RTS from B but it does not receive the CTS from A because C is not within the range of A. So since the CTS is not heard by it but it only heard the RTS, it obviously means that it is not near the receiver, so it can begin its transmission. So C could transmit to D. So we are also solving the exposed node problem by making use of this particular mechanism. So the RTS and CTS are our solution. Now RTS and CTS will both contain length of the packet to be sent, so others know how long to wait. Now obviously the moment I have heard an RTS and I decide that I am not going to transmit, it obviously means that I hear a CTS and I am not going to transmit, it obviously means that I am not going to transmit for quite an amount of time. So how long do I wait before I try to transmit? That I ascertain by looking at the length of the packet which is contained in both the RTS and the CTS. So that gives me how long I should wait before I can try to access the media and try to transmit. So we solve both the hidden node problem and the exposed node problems by this mechanism. So you can look at what will happen over here. So I have the source transmitting to the destination. So you first start with an RTS, a request to send. This sends back a CTS, a clear to send, and then you start with data transmission. Once the data is over, you get back an acknowledgement. Note that there are some interface spacings that are shown over here. That is, as soon as I receive an RTS, within a short interframe spacing, I send back my CTS. Similarly, within that same short amount of time, again send the data, and after receiving data, within a short amount of time, I send the acknowledgement. Now all the other stations during this entire duration go into an AV state which is called the no carrier sensing state. So once we have this, let us look at how the 802.11 MAC sublayer protocol will work. So you can see that A will send an RTS, B will send a CTS, all the other stations C and D during this time, okay, they go into the NAV mode because the data transmission takes place over here. Then once the ACK is received, NAV ends and then again they can start the transmission. So this is how the MAC sublayer protocol with the help of the RTS and CTS solves the hidden node and exposed node problems and takes care of media access. We will take a short break now and come back and look at the other details of the 802.11 protocol. Welcome back after the break. So, we have been looking at the 802.11 protocol and the media access control protocol that is used on 802.11. So, we said that it uses the media access control with collision avoidance. We talked about something called a hidden node problem and a exposed node problem, and we saw that how by using a simple mechanism of RTS and CTS we have solved the problem. There is one more question that you can ask in that kind of a situation. What happens if two people transmit RTS at the same time, because those two RTSs then can collide at a particular receiver. If they collide at a receiver, what would happen is both the nodes which transmit an RTS will not receive a CTS. So, since nobody receives a CTS, they will both back off, use the same exponential back off technique, come back and try later, and then finally one of the RTS will succeed, and then the entire process will continue as specified in the 802.11 protocol. Okay. So, now coming to the architecture that is specified for how an 802.11 network is expected to be set up. Okay. So, what we have for the architecture is we have what is called as a distribution system or a distributed service set, DSS as it is referred to, and through multiple access points there you have multiple BSS or a basic service sets which are connected. So, you have the entire wireless range divided into multiple basic service sets, okay, which are connected by means of an access point. So, all the nodes which come within a BSS would be within the range of an access point. So, they would all talk to the access points, and these access points in turn are connected by means of a distribution system, and which in turn could be connected to a server or a gateway and to the internet. So, this basically is the architecture of a 802.11 wireless network. That is, you will have DSS and then you have various BSS which are connected by means of an access point. Now, these access points are connected by means of a distribution system. This would be a wired network, these here are a wireless network. Now, so what we basically have is that within a BSS, nodes could be talking to each other, or they could talk to other BSS through the access point. So, when you have to go from one BSS to another BSS, you would go through this access point, through the distribution system, and then back to the access point over here. This access point then would transmit the data to the corresponding destinations node. So, this is the idea that is used. But within BSS, what exactly are the functions to be carried out? In the distribution system, what are the functions to be carried out? These again are defined in terms of the protocols that are used for each of these layers. Okay. So, so you could also have just a basic service set without an access point, that also is supported in this architecture. I could have an AP, an access point, and use this AP to connect up to other APs, or I can just set up a simple 802.11 network even without any access point. So, in this case what I will have here is, you can see this, just 4 stations or n number of stations connect, they can just talk to each other, okay, without even the use of an access point. So, you would say that they work in what is called as an ad hoc mode of operation. So, this is a possibility, or you can have a structured or an infrastructure based mode of operation, where you have an access point which provides the infrastructure for them to talk to each other. So, these are the two options that are available for us. Okay. Now, coming back to the transfer of data with the distribution system, okay, that is, we are looking at the infrastructure based data transmission. So, let us say we just have some nodes A to H, okay, and now remember that these nodes, not only are they just wireless nodes, they can also move, they are also mobile nodes. So, I said we can set up mobile nodes, mobile networks using this 802.11 framework. So, let us say for instance, we have some nodes here A to H which can actually roam around, okay, these nodes here can actually move around. So, now some nodes are wired together which are the access points. So, these access points will be stationary, okay. So, these APs are the ones which are connected to the distributed system as we talked about, okay. Now, the 3 regions that are shown are more or less like cells that are used in a cell phone network. So, 2 nodes A and B could communicate with each other directly, but in practice they would go through the APs. So, the path from A to E in this example would be A to access point 1 to access point 3 to E. So, just take a look at that. So, from A I go to access point 1, from there to access point 3, and then from there to E. So, this is how I would go from A to E. Okay. Now, let us look at how a node finds out the access point. Now, that is an important thing to look at. That is, how does a node know that this is the access point to which it is connected, and especially when it moves from one range to another range. So, for instance, let us say A moves from this position to somewhere towards the end over here. Now, as it moves from here to here, when it comes out of the range of axis point 1, it will lose contact with the axis point 1, then it will have to associate itself with another axis point, let us say axis point 2 in this case. So, let us look at how this association of nodes with axis points takes place. What a node normally does, let us say for instance a new node has now come in, okay, and wants to be connected to this wireless network which exists over here. So, what the node will do is that it will send what is called as a probe frame, okay. The node sends a probe frame, and then what will happen is all the access points within the range of that node respond with a probe response frame, okay. For instance, let us say B was the new node that came in over here. Now, look at B is within the range of AP1 and AP2. So, when B sends a probe frame, both axis point 1 and axis point 2 would send back their probe response frames, okay. So, then what will happen? The node now selects one of the APs and sends that AP an association request frame. Now, B has a choice now to either associate with the axis point 1 or with axis point 2. So, B can choose one of these, it could make the choice depending on the signal strength and so on, that is you can use that particular choose that access point which has a higher signal strength. Of course, when you receive the signal strength, you can look at the received signal strength and choose one that has a higher received signal strength. And so, it chooses one of the access points and sends that AP an association request frame saying that I want to be associated with you. That AP now will reply with an association response frame. Okay. Once that association response frame comes to B, B knows now that it is connected to that particular access point. Okay. So, this is one mechanism by which nodes can connect to an access point. In addition to this, there is also one more mechanism available. Okay. This particular mechanism is called as a active association mechanism. The other mechanism I am going to talk about now is called as a passive association mechanism. Here what we do is the APs, the access points, they periodically send a beacon frame that advertises that they are available. That is, an AP will go on sending some beacon frame. A beacon frame is something like saying, okay, I am available, these are my capabilities, right. So, it just keeps on sending that information. So, when an AP sends this kind of beacon frames, in response to the beacon frame, a node can now send its association request frame, and then it gets an association response frame as in the case of the active mode of operation. Okay. So, both these modes of operation are available for a node to be associated with a network, with an access point and then connected to a wireless network. So, this is the another important aspect of our 802.11 protocol. Okay. Now, if you look at the MAC layers that we have in the IEEE 802.11 standard, now we saw that we have a physical layer and then we have two different things, right. We talk about an access point that is used and we also talk about a distributed system that you have. So, for the distributed layer functions, you have something called a distributed coordination function or the DCF MAC functionality, and then you have a point coordination function which is the PCF, which can be optionally used by the access point to talk within the range of that particular access point. Above this, of course, you will have the logical link control sublayer, which will take care of the data link layer operations. Okay. So, we are more concerned with the MAC, so we are concerned with what will happen at this layer between the point coordination functions and the distributed coordination functions. That is, all the functionality that is required is handled at these two layers. When we talk about media access control and media access control frames, there is one more important aspect that is used in this 802.11 protocol, which is called as interframe spacing or IFS as it is referred to. So, if you look at this IFS, what basically is an IFS? It means that from the between two frames there is some short gap that is used, so that one frame will not collide with another frame. Now, what should be this duration of this gap? That is what we are trying to determine. What 802.11 does is it uses different values for the gaps. That is, we have what is called as a short IFS or a short interframe spacing, which is used whenever control frames are used. Okay. And then whenever PCF frames are used, that is point coordination function frames are used, we use what is called as a PIFS, PCF interframe spacing. Whenever distributed coordination function frames are being sent, DCF frames, they use DIFS, which is a DCF IFS. And then you also have an error recovery frame which uses an EAFS before it can be transmitted. So, what we mean by this is that whenever control frames are sent, they are sent within an SIFS time, that is, or immediately after an SIFS time. Whenever a PCF frame is sent, it is sent after a PIFS time. DCF frames similarly are sent after a DIFS time, and error recovery frames are sent after an EAFS time, and you order these times such that SIFS is less than PIFS, is less than DIFS, and that is less than EIFS. By doing this kind of an ordering, what you actually get is that you get some kind of a priority for the frames that are sent. Since the SIFS frames, remember that SIFS is less than PIFS. So, if I want to send if a particular node wants to send a control frame and another node wants to send a PCF frame, okay, note that the SIFS being shorter than PIFS, the node which wants to send a control frame will do its transmission before. So, by the time the PCF frame tries to access the media, it will find that the media is already busy because there will already be a transmission in progress. Okay. So, this is something that is used in order to provide some kind of priority to different data frames that you have. So, you can see that control frames will have a higher priority. The next priority is for PCF frames, that is where the access point wants to, let us say, poll the different nodes that are there in the network and so on. So, that will have the next priority. Then you have the distribution control function frames, so DCFS. Then you have the error recovery frames. So, this is the ordering that is used for the frames. So, if you look at this, you can see the same thing. So, and I have an acknowledgement over here, right. Once the acknowledgement is over, a control frame can start immediately after an SIFS time. Okay. A PCF frame can be sent over here only. A DIFS frame can be sent, I mean after a DCF frame can be sent only after the DIFS spacing, so it can be sent over here, and a bad frame recovery or an error recovery can be done only over here after the EIFS spacing. So, you can see how this interframe spacing helps us to space out the different functions, different frames corresponding to the different functions that we have over here. Okay. Now, coming to the frame format, now this is another important aspect that we need to understand. The frame contains the following fields: a control field, which tells you, I mean, okay, you have different types of frames first. A control field is a frame carrying data, or is it carrying RTS or CTS. You can have a control frame and you can have a data frame. So, you have a control field which tells you whether it is carrying data or whether it is a control frame. That is one of the fields that you have. Then you have a payload which can be up to 2312 bytes of data. Then you have a CRC, checksum of the packet, and then you have different addresses. So, it is possible that the packet needs to be sent across the distribution system, in which case we keep track of the original sender and the original receiver, but we also want to know the intermediate senders and receivers. So, we do not have just two addresses, not just the source address and destination address, but we also keep track of the address of the access points through which it has to be sent. Okay. So, it is not one address, but you find that you will have 4 different addresses which are actually used in the 802.11 frame format. So, this is one of the major differences that you have from the 802.3, 4 kind of and 5 kind of frame formats. So, if you look at the frame format, so you will have a control field here, it is a 16-bit field. Then you have a duration field, which is a 16-bit field again. Then there are address 1, address 2, address 3 and address 4, which are 4 48-bit fields. Then there is a sequence control field. Then you have the payload, which can be from 0 to 2333 bytes. That is followed by the CRC, which is used for error checking, which is a 32-bit CRC that is used over here. Okay. So, these are the fields that you have in the frame format. The subfields in the frame control field, okay, are like this. It will contain the current version, information about whether it is a management field or a control frame or a data frame, and then there are subtypes which tell you whether it is going to the distribution system or whether it is coming from the distribution system, whether there are more fragments are going to follow this particular frame, whether this is a retransmitted frame, whether it is a power management frame, and whether more data will be sent, whether it uses the wired equivalent privacy for security and so on. Okay, there are many such bits which identify the different functions that need to be carried out by this particular. The 802.11 protocol is a very large protocol. So, there are different functions that need to be carried out. So, this FC field tells you what kind of information is being carried in this particular frame. Okay. So, if you look at the control frames, now these are important things for us, the RTS and the CTS or rack. So, this will consist of the FC, frame control, duration, and it will only have 2 addresses, address 1 and address 2, right, and that will be followed by the FCS. CTS frame on the other hand similarly will have FC, just the destination, okay, so duration, and only a single address for sending it back only to the one which sent the request, and followed by the FCS, which is the 4 bytes. Now, another important factor that we talk about is the use of the 4 address fields. So, just quickly look at what these 4 address fields are used for. So, when I am sending it from a DS, if the 2 values are 2 DS and from DS values are 0 and 0, it means that I am just sending it from a source station to a destination station within a single BSS itself. So, the address 3 field there just carries the BSS ID. If I am sending it, if the values are 0 and 1, it indicates that I am sending from a source station through to a destination through a particular access point, and so the sending access point's data address is carried in the address 2 field. Similarly, the third option is that you have a receiving AP, you have an AP which is receiving the data. So, I have a source station, the destination station, that that information is carried in address 2 and 3, and receiving AP information is carried in address 1. Similarly, if the values are 1 and 1, it means that receiving AP and sending AP, there is the sending AP is sending it to the receiving AP, and it also tells you who is the source destination, who is the destination station. So, you can see this over here, that is A is just sending it to B within a single BSS. You only have A and B information being stored over here. Address 3 consists of the BSS ID. Now, let us say the access point is sending it to B. So, in which case access point sends to B and says from whom the data is being sent. The other is A is sending it to an access point. So, A says I am sending it to the access point, it also says to whom it is supposed to be sent, that is B over here. Now, here an access point is sending it to another access point. So, you have AP1 to AP2 as the main addresses, and it also consists information of who is the original sender and who is the original receiver. Okay. So, this is how you handle the sending of frames from one access point to another access point. So, with this we can summarize what we have been looking at today. So, we have looked at the physical transmission techniques used for spread spectra. We have looked at the range of nodes limiting the transmission and reception, the hidden node and exposed node problems, and how RTS and CTS are used to solve this problem. We have looked at 802.11 architecture and how it works and the different frame formats. So, we have a set of questions for you that you can review in order to see if you have understood what we have been covering today. So, what do we mean by a hidden node and exposed node in a wireless network? Question number 2, why do they cause a problem in media access? Question number 3, how does the CSMA CA solve that problem? Question number 4, what is frequency hopping spread spectrum? Question number 5, what happens in direct sequence spread spectrum? 6, what is a BSS? 7, what does an access point do? 8, how does a node associate with an AP? 9, what is a beacon frame? Thank you.